topic, which is the optimal transformer monitoring that includes key principles, fault-driven approach, fault parameter metrics, monitoring configurations, best monitoring practices, and then finally we will end our webinar with current central condition monitoring architecture and future architecture or future approach on central condition monitoring that includes industrial Internet of Things, IIoT, and cloud implementation. And we will briefly touch on the gateway with analytics.
Okay, and if we didn't have enough difficulties already in the beginning, I am going to attempt to launch a poll. So we would like to understand from the audience that is actually here on the line, how many of you are currently doing condition-based monitoring on your assets? And I know everyone has different definitions, so for the basis of this poll, let's just say a combination of sensors and monitors. So we just want to make sure that we're catering the content to the audience that's here today. We're good.
Sorry, everyone. Sorry for this delay. So no more polls then, Haley. Okay.
Absolutely not.
Okay. So as I was discussing with you that the trend on the continuous online monitoring, the trend started with the collecting the raw data, which requires higher expertise in identifying the health of the transformers from that raw data. Then utilities moved from collecting raw data to the collecting diagnosis information. So diagnosis information means adding advanced sensors on top of raw data sensors or on top of basic sensors. These advanced sensors, some of the example of the advanced sensors are dissolved gas analyzer, bushing monitoring system, and partial discharge monitoring system. And these advanced sensors has diagnostic built into them, and they provided like fault type on the transformers, criticality of that fault type. So it required less expertise in identifying the asset, the health of the asset. But still it wasn't enough to understand what needs to be done in terms of replacement of transformer, what needs to be done in terms of taking decisions on maintain versus operate versus replace. So utilities later on moved to identifying or calculating analytics from raw data and diagnostic data in combination with the offline testing data. So these analytics involved asset health index models, criticality index model, probability of failure, risk index models, maintenance index models, and most of these models are driven by, at present, they are largely a manual process. So what utilities are doing is they are collecting offline testing data, periodic online monitoring, continuous online monitoring data, and manually calculating the asset health indices, and these finally utilizing these asset health indices on long-term maintenance and asset investment planning. In terms of data points, so next comes to how many data points utilities are monitoring. So here what we have done is we have combined all the data points currently utilities are specifying into their specifications, or condition monitoring suppliers are asking utilities to monitor. So if you see the total number of data points, you will be surprised to see that the total number of data points has already reached up to 150 data points from the transformers. And these 150 data points are from 50 different parameters. So those 50 different parameters are covering the all key component of transformers, main tanks, bushing, OLTC, cooling system, magnetic circuit. So if you combine all of these components, if you monitor all of these components, people are asking utilities to monitor up to 150 data points. And this data points is never reducing, it's always increasing. And with this increasing amount of data volume, are you guys actually able to realize the value of the monitoring? Are utilities actually able to detect the fault, save the transformer failure? If we ask this question to the utilities, what we get is still they are not positive. They are facing challenges. And those challenges are mainly broadly related to either they are having doubt in terms of accuracy and benefits of the condition monitoring. Either they are not able to, the condition monitoring systems are not able to capture the fault, and even if few data points are capturing the fault, the alarm is hidden between 150 data points, and it's not giving a direct indication to the customer or to the utilities that yes, you have the problem, and these alarms are not being acted upon. And even more the growing problem is false alarms. Utilities are still thinking that the alarm is not 100% accurate alarm. So this is the major problem at the moment condition monitoring on the transformer is facing in terms of accuracy, in terms of monitoring. In terms of cost, definitely it brings a cost higher if you monitor more data points, and the cost in terms of installation of the material, in terms of installing monitoring system, in terms of maintenance, in terms of operational cost, every year the cost of monitoring system is increasing. And if you see now, in fact, utilities are making a joke that now they need to put a separate cost for maintaining the monitoring system rather than maintaining the assets. So this is becoming another important concern or challenge for current monitoring. Then coming back to the data management, definitely the data management is in terms of data storage, in terms of data mining requirements. If you are monitoring 150 data points from the transformers, and even if you are monitoring only 100 transformer, it becomes 15,000 data points. So definitely, first of all, how to store that data in a cost-effective way, and then how to utilize that data to convert the data into a meaningful information. The basic problem what we have identified, or what some of our customer have told, is the philosophy of condition monitoring. So what we have got, or what we have found out, is condition monitoring has been considered as a tool, or condition monitoring has been considered as a system. However, if you see the major definitions of condition monitoring, be it is ISO 55000 or PAS 55, the best asset management practices, they define condition monitoring as a process. So condition monitoring, in fact, if I just read out the PAS 55 definition, condition monitoring is a process or activity that determines the status of an asset, and the essence of the condition monitoring is to realize value through managing risk and opportunities. So definitely, in summary, condition monitoring is a process of collecting the data related to the condition of the asset. And that data can come from offline testing, that data can come from online testing. And after collecting the data, the next step on the process is next activity on the process is assessing the health of the asset, and then the final activity is utilizing that asset health in taking a decision on operate versus maintain versus replace. So that's the whole process of condition monitoring. And coming back to the condition monitoring tools, definitely the condition monitoring process, condition monitoring tool, it varies with type of the transformer, environmental condition where the transformers are being installed, uses of the transformer, operating condition of the transformers, and age of the transformer. So if I give you a quick example, like type of the transformer. So condition monitoring process for GSU will be definitely different than the condition monitoring on transmission transformers. Like as a direct example, GSU will not have the LTC monitoring. So definitely you will not do the LTC monitoring on the GSU. Similarly, environmental condition, the transformer installed on the colder region may not require enough moisture monitoring. Similarly, usage of transformers, if the condition monitoring on overloaded transformer will have to be much more comprehensive than the condition monitoring on underloaded or 50% loaded transformers. Operating condition, if you take an example of wind farms, the biggest problem with the wind farms is transients. So monitoring the transients on the voltage and current will be the bigger objective or bigger concern as compared to the transformers in the CCGTs or in the gas power plants. Age of the transformer, definitely newer transformer will have different monitoring requirement versus the transformer at the middle age versus the transformer towards the end of the life. Taking into the process, so the process is basically, if you see the monitoring, if you see how much monitoring you need to do on the transformers, it starts with how critical is the transformer, as well as how severe is that condition of the transformer. So definitely, if you will have more critical transformers, you will require more comprehensive monitoring in that transformer. And if you have less critical transformers, you may live with very small or very minimal monitoring on that transformer. Coming back to the severity of the transformer condition, so this examples I'm taking from some of our key customers, where what they are using is they are basically adding the condition monitoring based on the severity of the transformer condition. So for example, they start with offline testing, followed up by offline testing with the basic online monitoring. And this offline testing is being done on a periodic basis. And once the offline testing gives them a result which is showing them severity of the transformer condition, they move up in the hierarchy, up in the pyramid, and they move from higher frequency of line testing to periodic monitoring to continuous online monitoring. So in this way, they can do this thing for DGA, they can do this thing for partial discharge, they can follow the same process for bushing monitoring. So you guys can follow the similar process for any condition, any parameter on the transformers. So coming to the optimal transformer monitoring. So what are the principles of the optimal transformer monitoring? And these principles are, basically the principles are revolving around performance, cost, and risk. How are you managing your performance and risk with respect to your cost? And all of this balance is finally this balance should meet the business objective. And what are the business objective? The business objective are reducing unplanned outage, uptime activity, optimizing planned outage. So for example, moving from planned outage 6 months in a year to planned outage for once in a 2 year. Similarly, optimizing maintenance expenditure, defer replacement cost, increase equipment utilization, demonstrate compliance and social responsibility, improve organizational sustainability. So these are the key business objectives the condition monitoring process should meet. In terms of regulatory and legislative compliance, so definitely condition monitoring at present is also being driven by meeting these compliance of regulations and legislation. So for example, SF6 monitoring is being done to meet largely to meet the legislative and regulatory requirement. If you see in the next slide, what we are going to convey in the following slide is condition monitoring is not a one solution for all the transformers. It has to be it's a consultative approach. So every fleet of transformers requires a expert set of eye to look into that fleet, to look into the problems into that fleet, and then decide on what needs to be monitored in that fleet of transformers. What we have done is we have taken this study in Qualitrol, and with our experts and with voice of customers, we have come up with the solution for general transformers, which is predominantly which includes the transmission utility transformers. But the similar kind of exercise can be done for wind farm transformers, can also be done for distribution level or sub-transmission transformers, GSUs. But similar kind of approach should be followed for different customers or different fleet of transformers. So what we did is we looked into the data from multiple sources, CGRE, IEEE, EPRI sources. We also looked into regional, statistics like Australia, New Zealand, power grid in India, similarly power grid in China. So what we identified is what are the typical fault types or fault conditions a transformer can have. And based on these fault conditions, next step what we did is we tried to identify the key parameters that will be responsible to detect that fault. And based on that, what we did is we came up with the matrix, and that matrix defines the fault types for each component, major component of transformers, and then parameters that need to be monitored for detecting that fault type. And you have seen some of these examples in our webinar promotions. So today I'll be requesting Thomas, whose team has led this activity in Qualitrol. Thomas will be explaining about those parameters, those metrics, and he will be explaining about minimal and maximum monitoring on the transformers. But the principle is basically we focused into these components on the transformers. These components are magnetic circuit, transformer winding, transformer oil insulation, cooling system, transformer main tank, transformer bushing, and OLTC. Then we found out the major fault type of these components, and then we looked into the parameters. So I'll request Thomas to take over from there and explain what you guys did, how you came up with the best monitoring on the transformers, and share your thoughts.
Hi everyone, this is Thomas. I hope everyone can hear me. Amit, can you just confirm that?
Yes, Thomas, you are perfectly audible. Go ahead.
Very good. So I just take the flow. Thank you very much. And thanks everyone for just having the chance to have that presentation here, and to basically also to answer your questions afterwards. I'm really looking forward to that. And Amit just made a good introduction, so to say. What are the basic thoughts in order to look a bit more deeper into what is the right thing to monitor. And in that regards, we, as he explained, we were looking into the different parts. In these regards, we took the example of a transformer. In the different parts of the transformer, what you see on the screen here in the matrix, on the left side, you see the magnetic circuit, the winding, and later slides we will have some more. And then what can happen, so to say. We were looking into what can happen and what are the things we can look for. Because the reason for that one, and I guess everyone knows on this webinar, that the question is what I'm going to monitor. So usually when I get that question, my question would be, okay, so what is the thing you want to look for? So what is the thing you want to prevent? And that's, as we have seen before, it depends on the history, so to say, of the fleet. Depends on different parameters. For example, so how a transformer is operated, overload, not overload, depends on if I have a transformer maybe close to a capacitor banks, where he sees very often transients, and so on and so on. And these are the main things. So once looking into the different parts, then just let me take an example. So for if you're looking for the magnetic circuit, and we are thinking about that, we want to discover once we have a loss of core ground. So how are we going to do that? And in that regards, the thing is we have to find out first what's going to happen. For sure, if you're losing the core ground, it starts to spark, and so PD would be something very interesting for that. So UHF PD, so is a method, is a parameter you can use in order to detect that one. And core ground current, of course, if you do have the possibility to measure the core ground current, if the grounding, so to say, is brought out, then it's also a good possibility to do. And looking, once you have sparking, looking at least for hydrogen is also giving kind of an idea already. Putting these three parameters together, and that why is marked red here in that matrix, These are the key, so to say, the key parameters in order to detect these type of defect. And why 3 parameters? It's also a bit of a question of the confidence. So if, for example, you have a partial discharge monitor on the transformer and you just get partial discharge, you most probably want to know why. So if you get some more information, for example, that the core ground current just is changing in a way, and you have, of course, high hydrogen, then the confidence in drawing a decision that might be related to somehow the loss of core ground, that gives you kind of a higher confidence in making this assessment. So we are saying, or according to our work we have done and the information we collected, the red ones are the important ones. That's the principle of that table. So the question is, first of all, to repeat that. So what is the thing I want to look for? What is the thing I have experienced in the past? Or basically, do I have a new fleet? Then maybe I go for a more general approach if I have a transformer where I want to do something about it. And then I can look which parameter I want to cover, and according to what I want to cover, then that defines the monitoring or the parameters I have to look for. It could be in terms of monitoring, as we heard, or also in terms of some parameters in kind of periodic checks. But the red ones are the key parameters, and if we want to increase the confidence in the results, then the yellow ones can give us some further information. For example, loss of core ground. To stay with that, if you measure the core hotspot, for example, with a fiber optic, and you see an increase there, then of course, I mean, that could be connected to that one. That gives you another kind of hint in relate to that type of fault. Or if you have a big gas accumulation, so gas accumulation relay will give you also kind of an idea about that. So the thing is, as more parameter you have, as more certain you are what you're looking into. Just taking another example from the windings, just to make it a bit more visible. And then we can look into winding in excessive moisture in the insulation in the winding. So how are we going to detect that one? First of all, we know that we cannot direct, at least at the moment, we cannot directly measure the moisture in the insulation. So we need to have kind of an indication by the moisture of the oil, but that alone is not enough, because that is changing with temperature. You know, that's moving forward, backward in the insulation, out of the insulation, and most of the moisture anyways in the insulation. So we need also to consider the temperature. And then also what will help us is knowing the hotspot temperature, because that is the worst place where we have to look for. And additional, the ambient temperature and the top and bottom temperature, so to say, in comparison, can also give us kind of an idea, so to say. So that means combining these parameters, the red ones are the necessary ones, the absolutely necessary ones, in order to detect that. Coming to the next slide, there we will have some more parts: the main tank, a cooling system, the leak with the oil itself, and in order to find out if the cooling system is running, most likely a VGA will not help. But maybe measuring the activity of the pumps and the vents, whatever type of cooling you do have, or basically also inlet-outlet temperature, can give you kind of an idea how efficient your cooling system is working, and more important, will give you also a kind of idea once something is not working as it should be. So in order to to find out some failure in the pumps and vents, you need to measure the motor current, for example, and you should measure also the flow. So in that regards, you are sure that first of all motors running, and second is that you also know that the oil is flowing, which is important for just getting a cooling. Okay. Then if we go further for the next slide, there we have the very famous OLTC and bushings. We would have a pool, but I know we don't do that one, but it would be interesting. So what would be the most important part on a transformer in terms of preventing failures? Some would say bushing, some would say different, and that's also a kind of an expression that it depends on the history, it depends on sometimes on the manufacturer, that depends on how I drive the thing. And looking into the bushings, for example, if I want to detect some moisture mainly due to maybe the sealing is not working that very well on the bushing anymore, how are we going to detect that one? The offline methods is sometimes it's starting to be sensitive only once the moisture is just increasing quite high. But if we use, for example, the heating of the bushing by the transformer, then I might be able to do that one by an online method, so to say, in order to see the different behavior for wet bushings and dry bushings, so to say, under different temperatures. So that means the power factor or tank delta, which region in the world you are, is a mandatory parameter. And additionally, of course, some people take also oil samples, which is a bit, we have to be careful with that one because the amount of oil is not that big, but it could be also kind of additional help on that. And for oil impregnated paper bushing, also sometimes the pressure inside of the oil of the bushing can be measured. In that regard, when the power factor is going up, then you're talking about a kind of overheating due to the thermal runaway. Of course, it is quite far already, but there are some indications. So that are the important parameters for detecting these type of fault. And if you're looking for the online tap changer, of course, if you want to know if that one is working fine, of course, the switch over time, the motor power consumption, and these kind of things are kind of interesting. So that should give kind of just a rough overview how we put that table together and how that table can be used. So coming from a different approach, not to talking about what monitors we should put on, but based on the fault-driven approach. So what I'm looking for, what is basically the thing I want to prevent. And in order also to come up with a kind of a setup for what is a kind of minimum parameters we should monitor, and what are kind of comprehensive monitoring, also depending on the importance of the transformer, but also in terms of cost of monitoring system first versus cost of availability of alternatives, which we're talking about offline testing. So what makes sense? What is a cost benefit, so to say? Then a very interesting thing is also reaction time. For example, if you take a basically reaction time, how much time I do have until I have to do something. So if you're looking for the offline test, then often between the offline tests there is a lot of time. So I should look for things which basically giving me the time to react on it. And as we heard also before, the same thing can get more critical, so that might be important then to shorten the time, and the reaction time will be shorter over time. Then another thing is the speed, accuracy, and confidence level. We talked a bit about the confidence level by relating different parameters to each other. Speed is how fast I can detect the fault. And one is, for example, if you compare a DGA and the partial discharge, DGA needs some time that the gas is just distributing through the transformer. But if you have a partial discharge, for example, then a PD sensor reacts immediately. So the speed of detection is also kind of interesting in terms of how much money you want to put, so to say, in monitoring, or what effort. And another question is also need of advanced analysis. So what you're looking for, for example, bubbling temperature, for example, the whole thermal model of a transformer. And that's also interesting, because for that one you need some parameters. Otherwise you cannot calculate that one. And another thing is also, if you have a new transformer or a retrofit transformer, that makes a difference, because in retrofit transformers you may have a limitation in terms of what kind of sensors I can put on it, or basically what kind of information I can get from that transformer, because I only can get that information, so to say, what is available or what I can fit afterwards. For a new transformer, of course, I can define it by myself. And that brings us to the next slide, which is giving kind of where we try to giving kind of an overview. What is a meaningful monitoring? I mean, each monitoring, even if you're looking for a minimum monitoring, should give you a result, because otherwise it doesn't make sense to put it on. And so a minimum monitoring, and then also separating the retrofit transformer from a new transformer. And in that regards, if you look at the parameter, and that's also a bit based on what kind of the statistic is saying, what is going to fail on a transformer, without that can vary, of course, according to the own history. But just an example set of these for the minimum monitoring could be just looking for the H2 and moisture, because moisture is one of the most important thing, and H2, of course, is increasing once you're having some problems in your transformer, which are happening in oil and are related to higher temperatures. Then thermal model. By the way, the input parameters for these models you can see on the bottom of the slide, so I don't go too much into that. And then tank wall and OLTC vibrations. So what is that's also a good figure in order to find out if, for example, you have a problem after a through fault, if your clamping forces of the transformer winding is still okay. And of course, a lot of people just having problems with bushings, and bushings basically are not so very expensive, but in regards to the damage they can do to a transformer, of course, they are very important that they are working properly. And OLTC, as you have a online on-load tap changer, so to say, then it's also interesting because that's the only part which is moving inside of the transformer. Going further in terms of comprehensive monitoring, of course, you're looking maybe for more gases than only just H2 for an important unit. Then you go also for the gas accumulation rate, load current and voltages, which you have anyway, most of the transformers. Core ground current, as we discussed before, inrush and fault currents, which is basically just getting the operational parameter into account also. Comparing now the retrofit and the new transformer, and the big difference there is just putting UHF partial discharge monitoring. We can discuss why UHF, but I think the time is a bit too limited, at least during the presentation. But if there are questions, we can answer that one too. But UHF PD monitoring has advantage that is just basically if the PD is happen, you get that the reading immediately. And the same thing for the comprehensive monitoring. And the UHF is added only for a new transformer. You can do it also for a retrofit, but it's more difficult than to do it for a new one. At a new one, you can always specify things in you want to have. For a new one, you have to add it in a way. And thinking about the sensors, they are kind of intrusive. So that means in terms of talking about new transformers, that's much more easier. So that's basically kind of kind of overview what work we did and what basically our approaches in terms of selecting the right parameters or selecting parameters for different applications of transformers and the different size and different importance, and of course also for different costs and different efficient. And with that one, I just want to give back to Amit, and he is going to conclude further this presentation.
Thanks, Thomas. Thanks a lot. Am I audible again, Thomas?
Perfect, Amit.
Okay. Okay. So with this background or with this research we have done in Qualitrol, I just want to summarize what should be the best practice on the monitoring. So again, these are the best practices we have discussed with multiple customers who have been implementing condition monitoring into their fleet. So we are just sharing our experience with those customers and where we have found it better while we were part of the implementation team. First and foremost thing is one solution approach. So mostly if you guys go with one vendor, one solution approach, then it helps you in reducing the project management cost, it helps you in reducing the integration cost, and during the operation of the condition monitoring system, it helps you in the reducing the maintenance cost. As Thomas mentioned, installing all sensors on the new transformer. So even if you're not going with the comprehensive monitoring, you must have a provision to install the sensors in future. So for example, if your severity of the transformer fault becomes towards the higher side, at least you should have option to fit the monitoring system. But if you don't have sensors, you won't be able to fit the monitoring system. So definitely for the new transformer, we strongly recommend that you should be having a provision to fit the sensors very easily. Then have the modular approach of monitoring. So modular approach means you start with the minimum. So for example, you start with only the thermal monitoring and bushing monitoring. And then you go with a solution which is field upgradable. So tomorrow, if you see you have more gas content, you can add DGA monitoring into that. And adding the DGA monitoring should be an easy field upgradable solution. So it should, your operation of the asset, operation of your transformer should not interrupt, or even if it is interrupting, it should be very, very minimal interruption. So always go with a monitoring system which has a modular approach and which is field upgradable. And finally, it should support advanced analytics. So as Thomas mentioned, that your partial discharge monitoring sensors, monitoring systems, your vibration monitoring systems, all of these monitoring system requires advanced analytics tool. And definitely if your monitoring system is capable enough to do the artificial intelligence, neural network based analytics or analysis tools, these models or adding these parameters will certainly help the monitoring system and will certainly help you in future. And the beauty of these analytical models or our neural network based analytics is most of them are self-learning algorithms. So self-learning algorithm means as they collect the data, they keep on learning from the data collection and they keep on refining themselves automatically. So we are moving towards the end of the presentation. So towards the end of the presentation, the last 3 slides I want to just cover once you have done the transformer monitoring, what is the next? How can you realize that value in a maximum way? The next approach is move towards the central condition monitoring. So you are collecting data at each transformers, then collect the data at the one central location, so that once the data is coming to the central location, you can utilize that data in your asset management practices and in your maintenance management practices. So asset management practices means once you have the data, you can rank the asset based on the risk index or health index and look for your optimal replacement schedule. So effectively you are maximizing your capital expenditure or you are optimizing your capital expenditure. Similarly, if you have data from all the transformers at one center location, you can plan your maintenance in an efficient way. So once you are going to a one substation, and if in that substation another transformer is going to have the health index, or going to have a lower, or going to have a higher risk index in next 1 month, probably you can do both the transformers in the same visit. So this is how, once you have the central condition monitoring, you can optimize your maintenance planning, you can optimize your asset investment planning, and you can optimize your asset performance. And the big thing is that data, that central condition monitoring system, wherever it is installed, whether it is installed into the headquarters or it is installed somewhere in the cloud, that headquarter-based central condition monitoring system should be collecting data from online condition monitoring system, from offline condition monitoring, offline testing tools, and from your maintenance and inspection records. So if the central condition monitoring system is having a data from multiple data sources, your asset health index will become more accurate. So if we think about the future, where the utilities wants to go ahead, they want to move to a cloud. So for example, at the moment they are storing data centrally into their headquarters. Some of the utilities have started putting data into the cloud, and this data is not mission critical data or control related data. It is a condition monitoring related data. You can probably utilize the benefits of the cloud storage, and the benefits, and that cloud storage could be on-premise cloud, or it could be a public cloud. And once you have the data at the cloud, you will have flexibility to use best-in-class analytical models available in the industry. And that those analytical models could be from one vendor, or it could be from multiple vendors. So it will definitely help you in reducing the cost of data storage, reducing the cost of implementing analytics, and it will give you opportunity to use multiple analytical models so that your planning becomes more accurate. And finally, once you have come up with the accurate planning, you can integrate this system with your workforce management system, and this integration will help you in automatic work order generation. A work order can be generated automatically based on the health of the transformers, based on the alarm condition, and it can directly go to the maintenance manager or maintenance engineer, and maintenance engineer knows what they need, what he or she needs to do at site. So effectively, it is reducing a one truck load of finding what is the problem with the asset. With this approach, definitely your transformer monitoring system should support cloud implementation and industrial Internet of Things, IoT. Another feature what utilities nowadays, I'm seeing at least few of the utilities have spoken to me or spoken to us, is they want to have analytics available into the transformer monitor. So if you see this architecture on the right hand side, I'm showing you the architecture. There is a transformers, and on the transformers you have multiple sensors. The sensors are connected to one transformer monitoring system, and transformer monitoring system is sending data to the cloud storage. So you have two approaches. Either you can send all the data to the cloud, or you can have basic analytics into this data aggregator or gateway, which could be your transformer monitoring system, and then only the result of the analytics goes to the cloud. And that makes sense to have this approach, because the customer or the user of this transformer monitoring system is the maintenance manager or substation engineer. And substation engineer is looking for faster alarm, faster response, faster decision making. And once you have analytics at the edge or analytics at the gateway, then you can move very quickly to the IoT platform. You can move very quickly to the industrial Internet of Things. And all of the features required by the substation engineers can be realized very quickly. And on top of that, it will reduce your network bottlenecks, because you are not sending all the data to the cloud. You are sending only the analytical output. And effectively, at the central level, when we are talking about the asset health index, we are talking about the risk index, we are talking about the probability of failure, only the analyzed output is required at the cloud storage. So again, whenever you're looking for the transformer monitoring system, these are the things you should be looking if you are looking from the futuristic approach. And this brings to the almost end of the presentation from our side. We are happy to take questions. Please go ahead and ask questions.
All right, we do have a couple questions, and I apologize for the webinar going over. I do want to do the quick giveaway because I know I am cognizant of everyone's time. So on my end, everyone who is on the webinar here is given a number, so I have a random number given away, or random number generator, I should say. So my random number is 34, and the name is Oscar. So Oscar, I'm not going to say the last name just for privacy, but I will send you a quick message and get your information. But you have won the Amazon Echo Dot. So with Amazon Prime, if you're in the U.S. here, you will get it in about 2 days here. So I will send you a private message, but we will start the Q&A session. So I do have the first question regarding LTC monitoring and online oil filtering. It seems people have not had great experiences for that. Do you have any suggestions for online oil filtering or LTC monitoring for those that have not had great experiences?
Thomas, you want to take the question?
Yes, I can take that one. Just one by one, maybe starting with online oil filtering. I mean, it's some utilities do that, and the thing is mainly that if you have a high gas content or high moisture, then of course you can clean the oil. But if you have a real, so to say, failure inside of the transformer, which is basically causing these high gas content, then of course you're not taking away the failure. You're just taking removing the output. And if you want to look for how the failure developed, and you're using a DGA, of course you're setting everything back to zero, and that means you don't see the development, so to say, of that fault. So that's a bit there's some pros and cons. It depends on for what you're using that. But if that is used to clean the oil for just because there is something inside which is creating these, then it's basically a kind of maybe not so good. But if oil, if you want to clean the oil because of other reasons, because of kind of heavy load or whatever, is kind of giving you the is making your oil bad, then of course that is kind of it's a good thing. And if you so that's kind of the approach in terms of online oil treatment. And in terms of LTC monitoring, yeah, that depends on there are different approaches in terms of going into DGA, but the problem with the DGA for at least for a oil type tap changer, of course it's creating the decomposition of the oil by purpose. So and is taking these in each tap changer, so to say, or each tap changer type oil type tap changer is just giving you a different fingerprints, so to say. So you have to really know your own tap changer type, how it behaves. The situation is a bit better if you're talking about the vacuum type tap changer. Then of course there is not because the switching happens in a vacuum chamber, so that means the oil is not so much contaminated, and you can assume that's basically more or less the same as just for the main tank. But what is more interesting also looking into the parameter of the OLTC is talking about the whole mechanical part, because what's going to be bad is the mechanical part. So what is the motor power consumption? What is the switching over time compared to basically healthy conditions? So these things are a bit more interesting and a bit more comprehensive in that regards. So that's kind of my experience in that two areas. Don't know if that answers the question.
Okay, great. Thanks, Thomas. We have another question. Do you consider new design and materials better alternatives to condition monitoring?
What was it again? Sorry.
Do you consider new designs and materials better alternatives to condition monitoring?
You mean improving the materials and the design of a transformer in order to prevent faults? I guess I hope that my understanding of the question is right. Well, of course, the condition monitoring aims for different directions, as Amit just also brought in his presentation. It's one part is detection of faults. The other thing is it doesn't matter which material you use, someone will get old. So it will have some failure mechanism. That might be a different type of monitoring, different type of asset assessment, so to say, needed for that. And monitoring, again, just remember we're talking about taking offline and online data. So that might be a bit different type. In a moment also, and don't get me wrong, but basically the things are getting or the price pressure on the market, especially also in the transformer market, is quite high. Not only there, of course, and that means it's also starting for the manufacturer for each type of equipment, so to say. It starts to be more difficult and more challenging, so to say, to compete with the competition. That's also just two things. So the focus in development at the moment, mainly at least as I know from my own experience, from my own past, is that the focus is mainly based on yes, using better materials, but also getting that one for lower costs, and so that's a bit going. Sorry, yeah,
absolutely. I agree with Thomas. See, design improvement or material improvement will certainly help in reducing the unplanned outage and increasing the reliability of the asset. But if you see the best practices of the asset management, best practices of the asset management, they enforce for condition monitoring. And condition monitoring is one of the critical component of best practices of asset management. And there are multifaceted advantages of condition monitoring. That includes your, reliability, increasing the reliability, or making notification well in advance about the fault, deferring the replacement, and optimizing the asset. Now, condition monitoring is being redefined by optimizing the utilization of the asset. So, irrespective of whether you have better design, better material or not, we consider that condition monitoring will be required.
Okay. Yeah, Amit, this question is for you. For bushings, does capacitance and loss factor, is that enough for, would that satisfy as being enough for monitoring?
That's a very good question. So that's why we have highlighted in our presentations, we have highlighted that bushing monitoring should be in your minimum as well as comprehensive monitoring, and especially we are talking about the reference method. We are not talking about the balance current method. So the idea is basically whenever you have the power factor and capacitance monitoring, these are sufficient to identify the issues with the bushing and help you to decide on the replacement of the bushing. So from our analysis, yes, these are sufficient provided you are doing the right kind of monitoring or right kind of measurement. And this right kind of measurement is you should be monitoring the absolute power factor and absolute capacitance. It should not be relative power factor and relative capacitance. If you're monitoring relative power factor and relative capacitance, definitely you have to go with the offline testing. You want to add anything on this, Thomas?
Yeah, I mean that's a big topic, and it's especially I used to work 10 years for bushing, so it's really, I mean I just can only emphasize what Ahmed was saying is for my experience, the power factor is or tank delta, depending on which part of the world, is a very powerful value, which is covering most of the types of defects you may experience with bushings, and which helps you to early detect, so to say, the developing faults in that one. Combined with capacitance, you can almost, well, you can cover a fair amount of the possibilities you have. And yeah, that's according to my experience.
Okay. Next question. How is the core ground current monitored?
May I? Okay, I just take that question. Core ground current, you only can monitor usually if the core ground is brought out of the transformer by, you do have that sometimes you have a small bushing on the transformer which is basically bringing out the core ground current, and that's grounded outside, and then you can for example measure the current with a Hall effect sensor, or yeah, in order to look for the continuity of the current, so to say. And if you have a change in that flow, then or kind of unusual behavior, then basically you can detect any unregularities. And but yes, if that one is not brought out, then it's rather difficult to do that, because if it is grounded inside the transformer tank.
Okay. Is there any system that can detect the quantity of corrosive sulfur and the impact it has on windings if the transformer oil is found to have corrosive sulfur in it?
Well, yeah, that's a whole discussion in itself. So the assumption of the industry is that corrosive sulfur, it's kind of the topic of the past, but obviously if you look at the works which are done at Sigre, that seems not be the 100% the reality. To detect that one, I mean, there are, so far as I know, there are no online devices at the moment available. That depends on, you have to take an oil sample, and then you have to look for this corrosive sulfur ingredients, so to say, in the oil. And what you can do also is kind of doing inspection of the winding, which is of course is a big effort, so to say, but that's what people do today in that regards. So as far as I know, there is no online monitor, or basically, yeah, online monitor available in order to do that.
Okay. How can you check that the transformer radiators are working properly?
Yeah, the radiators, you basically look for the power consumption of these motors from the radiators. So if that one is changing, or if that one is zero, so to say, then you can assume, or if it is too high in a way that basically something happened, something mechanically that the radiator is stacking, that is a way to do that. So the motor current of the vents in that case.
Okay. Let's see here. What are the electrical tests for detecting deterioration of windings and craft paper by the attack of, oh, it's another corrosive sulfur one. We can probably skip that one. Okay. Let's see here. Is there a way for online, is there is there a way for online monitoring tan delta on bushings?
Yes.
Yes.
Yeah. Amit, if you want, you can take over that question.
Yes, definitely. That's why we have put it here on our minimal and comprehensive monitoring. Tan delta is similar to the power factor, and there are multiple solutions available in the market which monitor tan delta or power factor of the bushing. And these monitors are available. Majorly, there are two different methods. One is measuring the relative value of the power factor and tan delta, and another method is reference method, which measures the absolute value. So here we are saying that you need to go for the absolute measurement of the tan delta or power factor.
Okay. Amit, this is actually going to stay with you. How successful is bushing monitoring effective for wind farm transformers, particularly with surges in line? And do these surges affect sensors or control circuitry?
For the wind farm, I'm not sure if wind farm will have capacitive bushings or not. Thomas, have you ever come across with the capacitive bushings on the wind farm?
Yeah, that depends a bit on the voltage level. Usually for these medium voltage, there I always use 16 or bulk bushings, depending again in which part of the world you are living. And these are just fully porcelain, nowadays also fully epoxy. Bushing monitoring is not applicable because you don't have a measuring tap. If you're talking about higher voltage and the use of capacitive control capacitor bushings, then yes, the transients are basically kind of not so good for the bushings usually. And in that regard, over time it can create a kind of a partial breakdown between the layers, and that can be detected by bushing monitoring. And the opposite question, or the other question, if bushing monitoring is used for that, then it needs to be protected for over voltages and fast transients, which are most of the systems are today. So I don't see any big thing, because usually you have the protection in the in this sensors you are screwing directly to the pushing tab.
Yeah, just adding on this, Thomas. Yeah, especially if you're talking about the wind farms. Definitely wind farm transformers is having a huge problem of transients. That's what we have got from our customers as well. And there, you should definitely go for transient monitoring, or in fact, power quality monitoring. So your transient monitoring or power quality monitoring could be one of the good options for avoiding such kind of failures.
Yeah, I mean, talking about the possibilities is also usually these transients are creating insulation failures, and over time, when basically they are just loaded with these transients, so to say, coming in very rapidly. And that means most likely it will create insulation failures in that way, which might be able to be detected. But that's I think there are some researches going on that. Could be a good possibility also to detect by partial discharge. So once the insulation is kind of infected.
And Haley, just on this, we can take a note of this participants. Thanks for asking these questions. We have done a paper on transients monitoring, especially for wind farms, and we can pass on this paper to this participant.
Okay, I'll make a note of that. Okay. Okay, I actually just wanted to let everyone know that it's 12:15, and to be cognizant of the time, there are a few other questions, but we can actually get you in touch with some of our application engineers, and we can address some of these questions offline just because of the time constraints. I will include the transient paper. There's been some other requests for some of the white papers that were mentioned here as well. So I'll actually include that in the email that will go out today. So you'll get a copy of those as well as the recording, and you'll get to obviously relive all of the lovely technical issues that we encountered earlier in the presentation, and you'll also get a copy of the slides. So please keep an eye out for that material later on today. And again, thank you so much for joining our webinar. And we do have actually 2 other webinars that are coming up this month. We have a webinar featuring our Tone software. It's regarding our dissolved gas analysis software. That is on June 27th. And then we have a webinar on fault recording as well on June 29th. So if you're interested in joining any of those, feel free to email me at info@qualtrocorp.com, and we'll be happy to sign you up. All right. Well, thank you very much, and enjoy the rest of your day.
Yeah. Thank you very much, everyone.
Thanks, Ellie. Thanks, everyone.